All right, so now that we have talked about heat and we have talked about heat of reaction, we are going to take this and apply this to very specific reactions. And this is going to allow us to calculate using stoichiometry the amount of heat involved in a reaction, or if I know how much heat's involved in a reaction, how much product or reactant there should be. So we're going to be taking a lot of these concepts that we learned previously involving moles, molar mass, stoichiometry, and then applying this new concept of heat to that. All right, so basically this is going to look very similar to what you have already done. We've already done the process of converting substances, grams to moles, and then using mole ratios to do stoichiometry. The only difference here is that we are actually going to start to incorporate and use delta H as a value to set up a conversion factor. And we're going to see exactly how to use that using the mole map. Okay, so here's our mole map, right? And so we have used this a whole bunch this semester. We've gone from grams to moles. We've dealt with we haven't dealt with gases yet, but we'll deal with gases a little bit later. We've talked about concentration, and we've talked about how to go back and forth between molarity and moles. And we've talked about Avogadro's number and how to go back and forth between moles and number of particles, right? So now where we're going to focus our attention is right here on energy and how we go from energy to moles, or if we know the moles, how we go from moles to energy. Now, a lot of times in these particular types of problems, these are probably going to involve mass as well. So again, you want to, if you have forgotten that how to go back and forth between grams to moles, you're going to want to give yourself a refresher, because we may have to go from grams to moles using molar mass, or go from moles to grams also using molar mass. So as we move on to the next slide, I would definitely recommend having your mole map out so that you can practice along and using that mole map. All right, so here is the reaction we are going to be taking a look at. This is actually the burning of octane. So octane is the primary ingredient in gasoline. So if you drove to school or you drove anywhere today, this is the reaction that allowed you to get there. All right, so in this particular reaction, I've given you the overall balanced equation, and I have given you delta H, right? And I've told you that delta H is negative 5,074.1 kilojoules. Now, the important thing to keep in mind with this, and we'll talk about our way through the mole map, this is part of your overall balanced equation. And so what this means is that when 2 moles of octane react with 25 moles of oxygen, that will give you 16 moles of carbon dioxide and 18 moles of water, and release that amount of heat. So looking at your mole map, right, so what I'm going to be asking for here is I want to know how much heat is released when 4.89 grams of octane is combusted. So I am telling you that we are burning 4.89 grams of octane, and the question I want to answer is how much heat is released. So if I think through my mole map and I kind of set this up for myself for exactly how I want to process and step my way through this example, I'm going to be starting with my grams of octane. Oops. Be helpful to write octane correctly. Telling you I am so on the struggle bus with writing today. Okay. So I am starting with my grams of octane. Now looking at my mole map, Anytime I start with grams and I'm doing any sort of stoichiometry, the very first thing I have to do is I have to convert to moles of octane. And if you look at your mole map to go back and forth from grams to moles or moles to grams, you want to use molar mass. All right, once I have moles of octane, now here's where things are just a tiny bit different than the stoichiometry you've done before. I have to get myself to heat. Well, my relationship here between the amount of octane and the heat is right in this balanced equation. I know that I have 2 moles of octane for every 5,074.1 kilojoules of heat. And so I want to use, this is going to come right from my mole map, right? This is where I'm going to incorporate that stoichiometry. All right, so in setting this up, I am starting with my 4.89 grams of C8H18. I'm going to use my molar mass, and I'm going to set this up in a way so that my grams will cancel. So I know I need to have 1 mole of octane in the numerator. And I'm going to put the molar mass on the bottom. And then remember, if you find the molar mass by adding up the masses of 8 carbons and 18 hydrogens. Okay. From here, I should always label everything. Now from here, right, so I've gotten to moles of octane. From here, I want to get myself to heat. I know that I have 5,074.1 kilojoules for every 2 moles of octane. And now I am exactly where I want to be. One thing I want to point out is notice that in the problem we told you that delta H was negative. Remember that that sign is just telling you whether it's exothermic or endothermic, right? I could completely rewrite this whole balanced equation and tell you that 5,074.1 kilojoules was part of my overall balanced equation, and it's on the product side because this is an exothermic reaction. If I had told you delta H was positive, then it would have gone on the reactant side of the equation, and it would be endothermic. But from here, I can just go ahead and plug all my numbers in and get my answer. Keeping in mind my significant figures, 4.89 only has 3 significant figures, and so therefore that's going to limit my final answer to 3 significant figures. So 109 kilojoules of energy is released every time I burn 4.89 grams of octane. Okay, I wanted to step you through one more problem, and this one's going to have us going backwards. So rather than starting with mass, this one is going to start us with heat. So in this question, it's how many grams of oxygen are consumed when 246 kilojoules of heat is released. So if I start to think about, okay, where am I starting and where am I going? I am starting with heat, right, or my energy. And from there, I have to get myself to moles. And again, I'm going to be looking here at that mole map, right? I'm going to be using my stoich, and I'm going to be comparing my moles of oxygen and the amount of energy that's released. Once I have my moles of oxygen, I can then go to mass of oxygen. And again, this also comes from the mole map, right? And I'm going to be using my molar mass to allow myself to go back and forth, or to go from moles of oxygen to mass of oxygen. All right, so let's go ahead and write this all out. So in this case, I'm starting out with heat. So I'm starting out with 246 kilojoules of heat. Oh man, I cannot draw a straight line. Oh, let's try that again. It's a little bit better. All right, so I'm going to use my mole map. I want to use stoic. And here I'm comparing my energy to my moles of oxygen. Again, setting this up so that the units I don't want go away, and I'm heading in the right direction, and the units I do want end up in the numerator. So I am going to say that I have 25 moles of oxygen for every 5,074.1 kilojoules of energy. And again, just like I mentioned in the last example, I am going to not include the negative sign here. That negative sign is just telling you that heat is being released and that this is exothermic. Once I have completed this step, my last step is to then go on to finding my mass. And so to do this, I'm going to use the molar mass of oxygen. I have 2 oxygen, so that's 32 grams of oxygen for every 1 mole of oxygen. And so now it's a matter of plugging my numbers into the calculator, and I get 38.8 grams of oxygen. And again, I can only keep 3 significant figures because my energy, 246 kilojoules, is only 3 significant figures. All right, so like I say, with just about everything, practice this. Again, this is not much different than the stoichiometry that you've done before. We've just added one more piece to that mole map.